My name is Klophaus. I'm one of the core engineers at Basho Technologies. Today I'm going to talk about a new feature we're adding to Riak called Secondary Indices. The whole sort of too long don't read version of this is that secondary indices fundamentally change data modeling in Riak. It allows you to model one-to-one, one-to-many, or many-to-many relationships more simply and more efficiently than you could ever before in Riak. But first, before getting to that, I want to dive a little bit into a discussion of trade-offs and NoSQL. So, by show of hands, you're going on an adventure. It's a quest. Would you choose to be a fighter? Nobody's a fighter. Would you choose to be a magic user, a magician? Okay, good. And how many people would choose to be thieves? Most people would be thieves. That says something about people that come to this conference. Maybe it's just the people who are interested in Riak. And how many abstained from voting? Okay. Well, the upshot is that if you abstain from voting, you're the only non-fool in here, because the real answer is that it depends. It depends which one of these you want to be, because the characters, it depends on their abilities, and it also depends on what your quest is. There's no right answer unless you know both of these things. So rule number one is that your character is going to fare better in certain environments depending on his or her abilities. And rule number two is that there are always trade-offs. You don't get an ability unless you're giving something else up. So the reason I'm talking about all this is because databases are a lot like role-playing game character classes. They focused on certain abilities. What are some of these abilities? Well, it's things like this. It's things like, does the database have a schema? If so, are you defining strongly typed fields in that schema? Can you just store a random blob of data in there? What's the operational skew that the database prefers? Does it like mostly reads, mostly writes, a 50-50 mix? Disk persistence. How often do you persist your data to disk? Is it after every operation? Is it in a batch? Is it after a certain number of seconds? Or does it just never write out to disk? Is it totally RAM resident? Things like transactions, data regions, operational order, secondary queries. Scalability is a big one. Can you scale across data centers? Or is your scalability limited to within a certain data center? Or can you even scale across machines? Are you limited to a single machine? So all of these things are different abilities that a database can have. For a long time, we as an industry focused on just one manifestation of database abilities. We focused on the relational database, and that's sort of what everybody talked about. And it made a lot of sense. Relational databases, they have a good balance of trade-offs. They were very adaptable to the problems we were trying to solve. Very mature technology. There are a lot of uses for them. They're a great technology. But the thing is that the world is changing. And I call this is my, should have gotten an MBA slide. I call this the mobile, social, global triangle. Because you need three of everything. So this is basically saying that the global internet and mobile computing and social networking, everyone is connected all the time, producing more data in more varieties than ever. And because of this, this is why we started looking at things like NoSQL. This is why companies started building NoSQL solutions to solve these problems and things for this scale of data that were a bad fit for the trade-offs and the abilities that relational databases have, but are a good fit for some of the abilities that these other solutions have. So NoSQL is all about alternatives, focusing on different abilities for different environments and different trade-offs, basically saying, well, what's your character class? What's your quest? Choose the right character for that quest. So the important thing is that a database consumer, you need to understand the basic trade-offs of each solution. And in turn, database producers should strive to make these trade-offs clear. And that's what I'm hoping to do for these next few slides. But the key thing is that there are always trade-offs, and anybody who claims that there are no trade-offs, and anybody who claims to do everything well, is lying to you. So, given all that about trade-offs, where does Riak fit? What abilities does Riak have? And as a result of that, what trade-offs does Riak make? It's the only time the flame transition actually makes sense. So the question is, have you ever been burned by hardware failure, or overloaded servers, or emergencies at 2 a.m.? Or does your quest involve SLAs that mention uptime or latency, or data that you can't afford to lose? If that's the case, then React's trade-offs are going to make a lot of sense to you. And if that's not the case, then they won't make sense. So let's look at some of the trade-offs that React makes. One of the trade-offs, or I guess one of the abilities that React has, is it's modeled after Amazon's Dynamo model, which means you get some great things like React is distributed, it's scalable, there's no single point of failure, hardware can fail, your system keeps running, your system stays read-write available. But of course, in order to get that, you have to give something up. And what you're giving up is that there are no transactions, and you also give up strong consistency. So you're working in a model of eventual consistency. Another trade-off. Basho, as a company, to this point, has been extremely focused on operations. So we've made React very simple to install, very simple to set up, very simple to connect to cluster. And in fact, if you want to scale out your system, you set up a node with Riak on it, type one command, and your cluster scales out. Conversely to that, but just as important, is that if you want to scale your cluster back in, you type one command, and a node drops out and it hands off its data to the remaining nodes. And this is very important because let's say you scaled up for some sort of event like the holiday season, and you've doubled the number of servers you have. Comes January 1st, you want to be able to scale back in and save all that money that you've been spending on servers. So we've been extremely focused on operations, and in fact, customers have called us plumbing in the sense that they install it, and it just kind of works. It's not especially sexy, it's just there, and it does its job really well. And that's what we strive for. But of course, to get something, you have to give something up. And one thing that we've sort of made the trade-off of to this point is that engineering hours, there are only so many hours in the day. Because we've been focused on operations, we've spent less time historically on developer-facing features. And I'm excited to say that that's something that's changing, and one of the ways that it's changing is secondary indices. But it's changing in a few other ways too. Third trade-off I want to talk about is that React chooses a key value model for data storage. Which basically means it's something you can describe to your grandmother. You associate a key with a value. If you want to get that value back, you provide the key. Very simple, very straightforward, very easy to teach somebody. The trade-off, of course, is that it's more difficult to discover your data. So it's very easy to get your data if you want to get it by key, but if you want to get it any other way, then it's more difficult. You have to overcome some challenges. So let's dive deeper into queryability. The current options for querying Riak at this point, if you need to go outside of the key value model, you have three different options. The first option is MapReduce. With MapReduce, you provide a starting set of keys, and you define an operation. So sort of the more general MapReduce is that you define a series of map and reduce phases, and you can process your data in parallel across the cluster. You provide a set of starting keys, runs in parallel across the cluster, and then you get your answer back at the end. And this in Riak can run real time. You can run multiple real-time MapReduce operations at once. But MapReduce is meant more for performing calculations and aggregations, and not queries. You can use it for queries if you define the MapReduce operation as sort of a filter, where you provide your starting set of keys, filter out the ones that don't match, get the rest back. But at a certain point, you're going to run into limitations. Picture if you have a cluster of 100 million objects and you want to filter across all of those. I don't care how parallel you are, at a certain point, you're going to have to read 100 million objects, do the processing on them, and kick them out the other side, and that is just going to take time. So that breaks down at a certain point. Another option that you have is Riak Search. Riak Search is a product we released towards the end of last year. And it's basically a distributed Solar and Lucene on top of Riak. It's implemented in Erlang from the ground up, but it acts like Solar and Lucene. And that gives you a number of good things, and of course a number of bad things, a number of trade-offs. The nice thing is it allows, of course, full-text search in Riak, and it models the Solar and Lucene model, if you're familiar with that. But the bad thing as far as just simple indexing is that Riak Search really forces you into that Solar and Lucene model, even if you don't need it. So it assumes it's very opinionated, it assumes that your document is prose, it forces you to use a schema, it makes you think about things like value extractors and tokenizers and what form your data is going to be in. And in general, if you don't need all of that, it's a complicated solution. So that kind of falls off the table as well. The last option that you have for querying Riak is that you can roll your own indices. So what you can do is you can actually say, well, if I have these objects that I want to store, I can actually make a bookkeeping object somewhere else and keep pointers to those objects with some sort of secondary indices. And then anytime I want to look up on that indice I just consult that bookkeeping object. That's a lot of code to write. It's difficult to get correct. It's sort of painful. An option that some people do, instead of creating that bookkeeping object, is to set up some sort of auxiliary system. So they might set up Lucene or a relational database or Redis or something like that, and store the index in there. But then you've introduced a single point of failure unless that external system is meant to run in a distributed failure-tolerant fashion. So we looked at this environment and said, all right, there are options for querying Riak, but at a certain point, all of them have flaws, all of them have trade-offs, and the trade-offs are affecting customers when they're really trying to do straightforward things. So we decided to introduce a new feature, secondary indices, and I'll get into that now. So the question is, and by the way, if I didn't say so already, if you have questions, just throw your hand up, get my attention. I'll be happy to answer them. What are secondary indices? The goal is to provide very simple indexing under Riak objects to maintain Riak's operational advantages. So to be distributed, scalable, failure tolerant, tolerate hardware failure, stay operational. And also to make a developer's life easier, especially when that developer is coming over from some sort of relational database to sort of reduce the shock of fitting into a key value model. How does that work? It's very simple. At write time, you tag your data with field value pairs. And at read time, you can query that. So you tag your data and it's stored as metadata. At read time, you can query that metadata to get back the matching objects. So to bring this back to an example, and to stick with our theme of role-playing games here. Let's say we need to store some loot, the gauntlets of shininess. We might store this in a bucket called loot. We give it a key of gauntlet 24. The value in Riak can be anything. It's an opaque object that we don't really care about, so this could be an image, JSON object, binary, we don't really care. The important thing for us though now is that we're going to add some index metadata to it. In this case, we could say, well, we want to be able to retrieve this object by looking up the category, or maybe we want to retrieve it by looking up the price. So we're going to tag it with a category and a price metadata. Getting down to the code, what would this look like to store this object in Riak? So here, this is an example of using our HTTP interface. I'm just going to use curl to interact with the system over a RESTful interface. The nice thing about Riak is that it has a fully REST-based interface you can use over HTTP. So what we're going to do here is we'll call the put method to put the object. The data, again, is going to be some sort of opaque value. We're going to add two headers determining how we want to index this object. One is the category, as I mentioned before, category underscore bin of armor, and price underscore int of 400. You'll notice that there are these suffixes here, underscore bin and underscore int. This determines the data type, the way we want to, the data type that we're going to use to index these fields. And finally, the endpoint is going to be /buckets/loot /keys/gauntlet24. This determines where in Riak the data is stored. All right, so we've stored that data. Now how do we query it out? Again, we're going to use curl for this, just right over the HTTP interface. We're going to query this based on the category equaling armor, and we get back the keys. Or we can query this based on the price being between 300 and 500, and we get back the keys again. So again, very simple interface, 2 slides to describe all that there is to it. And I'll say something else here. Actually, more generally, the query syntax looks like this. /buckets, the bucket is which bucket you want to query. The field name can be any name has to end in a suffix, underscore bin for binaries or underscore int for integers. There's also a special field, $key, And you can use that for key-based lookups, so for key ranges, less than, greater than, things like that. And finally, the operation, the different operations that you have at your disposal are the equals operator, less than and equal, greater than, equal, or a range. So let's get into how having this functionality changes data modeling in Riak. To begin with, I'm just sort of going to use the general key value lookup as a way to sort of introduce the syntax that I'm using here. Basically, the next few slides, at the top there is going to be sort of the use case that we're looking at. Below that is the more generic case of things. And then this diagram, this whole thing is the object with the key on the left and the value on the right. So let's look at how we can use secondary indices for doing alternate keys for an object or one-to-one relationships. Let's say we have an object, a user object, and we want to retrieve it by either the username or an email address. Without secondary indices, we would do something like this. We would have a user object, and we'd have the data contained in that user object. And in order to pull out, having this object allows us to look up the user by username. But if we want to get the user by email address, we would do something like this, where we'd have another object, and that would have the email address. We'd associate that with the name of the user, and then this would point us back to here, and then we'd get that. So we would have to think about sort of maintaining, creating and maintaining these objects down here in order to solve this use case. With secondary indices, that second object goes away. And instead, we would do something like this. We'd have our object, and we would just tag that with the indexes down here. So we tag it with an email _ bin index, and maybe a Twitter _ bin index. And then when we wanted to get the user by email address, we could do the query for the user by email address. So it simplifies everything. So let's look at one-to-many relationships. Something like this. A person has many cars. Right? And the more general case here we're going to look at is that the parent object has a small number of child objects. The reason I'm emphasizing a small number is because for this, you can see we've denormalized the data. So we're taking the child objects and sticking them right in the parent object, which is a common thing to do at a key value store. The nice thing here, of course, is that we can look up Frank and get all Frank's information as well as all the information about his cars. Of course, this has a limitation in that we can't easily look up the information about a car and then get back information about Frank. So with secondary indices, what we might do is tag the record for Frank and tag the different plate numbers for his cars. And we can look up, we can search on the plate numbers for Frank and get back the Frank object. Well, let's say that we can no longer denormalize that data. Let's say that the parent has a large number of children, such as the case with a user with maybe Twitter status updates. And what we don't want to do now is shove all of these status updates into the user object itself, because then this user object is going to grow unwieldy pretty fast. So instead, we might do something like this without secondary indices. We might have the user's object and store a list of all the different status updates that they've committed. And then later we would have, or in a different bucket, we would have the different statuses with the status text. So this is what it looks like without secondary indices. With secondary indices, we can get rid of all this bookkeeping information that we had up here. And again, we would just tag the status object with some information to find it easily later. Yes?
So what's the trade-off?
Good question. In what sense?
Well, I mean, you said that every feature has a trade-off. That was like a big part of your intro. So you've introduced a feature.
Yeah.
What trade-off does it introduce?
Let's see.
Or was this just low-hanging fruit that just hadn't been done?
Well, it's not in memory. I'd say that the trade-off, one part of it is that it was low-hanging fruit that hasn't been done. The other part of it is anytime you are, I'll say this, anytime you're providing sort of functionality or a framework for the developer or the user to work in, you're making certain decisions for them based on, on sort of what you think it should be. In this case, actually, I'll go back to this example here. Yeah, this is a good one. So in this case here, this is just doing sort of a one-to-one relationship. If we are maintaining our own indices here, we have this extra work of sort of creating and maintaining this object. But it does mean that when we want to look up this object, we know exactly, well, it's going to be one key value lookup here against a node or a few nodes of the system, and then one key value lookup here. We know exactly where to find this because we're referring to it by name. In this case here, we don't know on which nodes in the cluster this object lives. So we have to broadcast that out. We have to broadcast the query out to a covering set of nodes, and I'll get into that later.
Got it.
But yeah, so I guess a simple way of saying is that the trade-off is that you're hitting more machines anytime you need to look at the data.
Got it.
So yeah. Yes.
I'm guessing there's no auto magic way then when you're doing a put or anything else to update your key value that you also have to make sure you update your indices.
Oh, you mean when you're storing this actual object?
Right. Well, yeah. So or when you're making an update to it.
Yes.
So you do your initial put, you set some indexes, and then you're going to update an email address, for example. Then you also have to make sure that you send that header in for all of your puts.
Correct. Yeah. And the model, Riak's model is sort of remember it's a key value store. So there's no way to update these individually. You're dealing with it as sort of one opaque object.
Still for basket.
Yes, of course, yeah. So yes, anytime you update your data, you need to update the indices as well. Yeah. I saw another hand somewhere, maybe. Yes.
I think we probably get it covered. I think that was his question too. You just said that. So you're storing indexes in the same nodes that hold your key.
Correct.
So
yes.
That's why you have to then scatter the query.
Exactly. Yeah. And there are definitely trade-offs to that gets into the trade-offs between document partitioning versus term partitioning. Sort of, do you store your indexes right next to the document where they live on the node, or do you sort of have global indexes where you sort of index the data and then have the entire cluster be your index? There are trade-offs for each one. In this case, we're using sort of local or document-based indexes. It makes more sense for our usage here. Our search product actually uses global indexes because that makes a little more sense to be found for full-text search.
So I'm not sure if it's a global index, but the other route would have been to have it in a separate bucket for each of those index terms. So after to write the main data, you have to write each of those as a separate home at different locations. Now you're doing more writes.
Correct. Yeah.
Sort of like you're doing more network writes.
Yes. Yeah. And that's the trade-off. Yeah. Yes.
I don't know if you want to touch on this, but what's sort of the transactional kind of consistency aspects?
I'm going to touch on that, yeah. So, hold on one second. Let's see. All right, so the last thing I was going to talk about, I'll get back into the different relationships, is the many-to-many relationship. So let's say we've got sort of a membership information where a user is part of one or more clubs, and a club has one or more users. Without secondary indices, we would do something like this, where we keep track of the clubs that a user is in here, and keep track of the members that are in a specific club here. And nobody's laughing at these little jokes that I have here. But anyway, so we do something like this, and we'd have to, of course, keep track of the bookkeeping information on each different object. With secondary indices, we can get rid of the bookkeeping object, at least for one of these instances here. And it probably makes sense to get rid of the bookkeeping information on the more contentious of the nodes, right? So instead, we would just store the list of clubs for that user, and then we'd index on the clubs as well, and we could very easily find the user that's in a specific club. And this becomes important if you have, for the DC LARPing club, there's all 2 of us in there, so it's not going to be much of a big deal. But for something like a NASCAR fans club, where you can imagine, hundreds of thousands, millions of people, you don't want to be updating the NASCAR fan club object every time somebody drops into and out of the club. So you generally want to sort of choose the least contentious object to do your updates. All right, and this is where we get into some of the, yes?
Are there different performance characteristics? So, I mean, in your examples there, for if you have an email bin, that's one user to one bin,
Yeah.
or one record to one bin, whereas the club, you have fewer bins to many users into it. Are there different trade-offs there?
Could you sort of rephrase that?
So, I guess is there, like, when you would be architecting your system, if you had, does bin count, is there a scaling issue there, or how are bins stored themselves?
Okay. So basically, are you saying does it matter how many indexes you have on a specific object or even in total? I'll get into that a little bit later too. But for all intents and purposes, it doesn't matter. So you can sort of have an infinite number of indexes, sort of space permitting, I guess. But there's very little overhead for each additional index, and the way they're stored on the back end, they're stored in such a way that you only really pay a penalty for them if you're actually hitting that data on the read. So. All right, so what were some of the challenges here? The first challenge is that we did a little bit of overly ambitious prototyping, and there's sort of a blessing and a curse to the way we've architected Riak. It's very simple to sort of swap out components and change components and add interesting things. And we've also written in Erlang, which means that it's very quick for us to sort of stand up new functionality. And it leads to things like this, where we have early prototypes that have a lot more in them than we're eventually going to ship with. So the early prototypes had things like a SQL-like query language, which you may have seen on the abstract for this talk, sorting and pagination, intelligent caching, inline MapReduce, extensible data types. We went a little crazy and decided, after sort of looking at the functionality, to pull things way back for the next release in order to make sure that we're rolling out with sort of a simple set of features that people can wrap their head around, that we can document well, and that from there we look at what customers need and what people want, and sort of build things out, based on which features are going to get used the most. So this was not a technical challenge, but more of a design challenge, and we solved this just by ruthlessly cutting features and simplifying what we wanted to do. Challenge number 2, data types. So the question is, anytime you're indexing something, you need to know what data type you're indexing. You also have other challenges. If you're indexing based on one data type and the user changes their mind and says, well, this was an int, but now it's a string, or vice versa. Or if the user provides a data type of the wrong type. So they declare a field an int and provide a string. You need to solve those challenges. One way to determine the data type is by naming convention. And that's ultimately what we decided to do. So based on the suffix of the type, or of the field, underscore bin or underscore int, that's how we know what type it is. The alternative is to use some sort of a global dictionary or schema. And that gets complicated very fast, because then you have a shared state that you need to maintain and keep synchronized among a system that is ultimately about eventual consistency and not having shared state. So you have sort of that mismatch there. And then it makes it much harder to deal with things like the user changing the type. In a schema, the user can change the type sort of whatever they want to. If you use a naming convention to determine the type, then it's very obvious to the user that if they're changing the type, they need to change the field name as well. And they need to reindex objects that have the old type. Finally, we use a pre-commit hook to validate the data at the boundary of the system, so we don't let any bad data into the system using that. Challenge number 3, and this gets into the question a little bit about the cost of indexes. The challenge here is that Riak is a disk-based system. And the reason it is because we want to make sure that the data is stored on disk, persistent disk, and safe in case there's some sort of a power failure or nodes drop out or whatever. So this is a challenge because disk, at least compared to RAM, is much slower. So we needed to find data structures that are both very quick to write to disk while at the same time writing to disk in a way that we can query them very quickly later on. We actually ended up with something very SS tables shaped. It's a library called merge index that we wrote for Riak search. It's the thing that stores all of our indexing information in Riak search. We were able to repurpose it for secondary indices. We're also investigating something, a library called LevelDB from Google. I haven't done much work with that, so I can't say too much more about that. But some other people on the engineering team are looking into that. But the basic shape of merge index is that it's sort of has a hierarchy of caches. So you're sort of caching things in memory, dumping that out the disk. Once the segments get bigger, you're rolling them up into bigger and bigger segments. So it stores the index very efficiently on disk in a compressed format. So you need it. Yes?
It sounds like doubling array.
It sounds like, I'm sorry,
Sounds like a doubling array.
Okay. I'll have to look that up. Challenge number 4, atomicity. So one of the so the question here is because of the different ways that we're storing and accessing the data, we need to keep the key value data separate from the indexing data because the access patterns are very different. So the question is, once you've separated those two types of data, how do you keep them synchronized? And it's a challenge because you need to keep them synchronized through things like through nodes being down, or in a Dynamo system, partitions are when you're scaling up or scaling down, partitions and the data they contain are handed off to different nodes. So how do you make sure that the key value data and the index data is synchronized through all of those events? We solve this by making the key value object the authoritative data source. So basically, anytime we're moving that object around, we actually discard the indexed data and re-index that object on the new node wherever it might live. And finally, the last challenge is that the system is distributed, which is a challenge because, of course, if you're indexing data, the system is distributed, that index lives on different nodes. And I talked about this a little bit previously, but in order to consult the index, you need to read a covering set of those nodes. The good news is that we don't need to query every partition. We might not even need to query every node. We do need to be smart about which partitions we query. Down here, this very simplistic diagram is each circle represents a node here. If you're storing 3 replicas of your data, for instance, which is the default that Riak starts with, you'd have a copy of your data sort of if you're storing some data, you'd have a copy on maybe these 3 nodes, which means that when you're querying that data, you only need to query one in each of those sort of triplets of nodes. So you can sort of hit the orange nodes and skip the other nodes in order to do a covering set across your data. Of course, that gets complicated if there are nodes that are down or different things like that, or if you want stronger guarantees around what data that you've read. So that got very complicated very quickly. And that's something that we actually extended Riak Core, which is the distribution layer that we use. And it's basically a library that takes the non-key value parts of Dynamo and sort of re-implements those. We extended that with the ability to broadcast a command to a covering set of partitions, and that was Kelly and Klophaus. I'm not going to go into these slides due to time constraints here, but if you want to refer to these later on, this is just sort of how we index in the system and then what the query path through the system looks like. Let's talk about next steps. So the next step, of course, is to publish this code, to get it out there. We are an open source company, so the code is out on GitHub now. We've buried it a little bit just to sort of be able to develop without too many questions being thrown at us. But if you sort of spelunk enough and you're foolhardy enough, you can definitely get the code. We're aiming to get a beta version out soon, which basically just means that we're going to sort of package things up in a little easier way for people to set up and run, and hopefully get some good feedback out of that. And then finally, this will be included in Riak version 1.0 for the masses. So I'm very excited about that. The one slide that I include in every presentation I give that talks about a product at all is that API design is like sex. Make one mistake and support it for the rest of your life. So everything we do here, or everything I've said, is subject to change. We're still sort of nailing down the shape of some of these things, but I think what you've seen is basically what it's going to look like when we roll this out. Yes?
Will there be a protocol buffers interface?
That is in the plans, yes.
HTTPs.
Trade-offs. And then, of course, the shameless plug, a little bit about Basho. We're a distributed company, 30 plus people at this point. We're all across the country and parts of Europe. We do have home bases in Cambridge, Massachusetts, San Francisco, California, and Reston, Virginia. So if you're in any of those cities, definitely stop by and grab a beer with us. If I had to say one phrase that really sort of captures how we approach software development as a company, as an engineering team, it's that we hate downtime and we hate overtime. So we hate downtime, so we do everything that we can to prevent your database from causing your application downtime. And we hate overtime, so we do everything that we can to prevent your engineering team or your ops team from having to spend a bunch of time repairing things. Riak KV is our core product. We built it and we released it open source about 2 years ago, I think. About 2 years ago to the day, right? 2 years in August. 2 years in August, okay. So you can go try that out. And then we as a company provide support services and enterprise features around Riak. So that's our business. And finally, these various people from Basho are at OSCon. So myself, Mark Phillips, who's right over there, our community manager, Ryan Zazeski, who is in the room, and Tony Falcon. So definitely come and see any of us after the talk. And that's it. Thank you.